Hello, welcome. In this exciting lesson in physics, we're going to learn about the colors of light and refraction. Now, you can see in this picture right here, we have a prism and we have a beam of light coming in back here at the back that is white, and then whenever it's split out, it splits into all these different colors. So, there are many different colors of light, and this is how we see objects of different colors. So if we start here, let's look at the two spectrums of light. We have both the additive spectrum, which is where we project different colors of light onto a screen, and then we get different colors where they combine. And whenever we add all the colors of light together, we get white light. Sort of that one picture before, but only in reverse. Now we have another spectrum here where we actually get the subtractive colors, which means that if we use light filters, and then whenever we take colors out of certain lights, eventually we'll get to black. So if we talk about additive colors, the three primary colors of additive light is going to be red, green, and blue. Now, if I mix red and blue, I get a color called magenta. If I mix red and green, I get a color called yellow. And if I mix blue and green, and I get a color called cyan. Now, if I mix all three of them together, I get white light. So white light is composed of all colors of light. Now, if I look at the subtractive colors, once again, I'm using a filter to pull out different light waves that I don't want to see. Then the three primary colors are cyan, magenta, and yellow. Now, these are in contrast to what your art teacher tells you are the three primary colors, which are red, yellow, and blue. In fact, these are the subtractive colors, or the primary colors of pigment. And you see these in your printer. Now, your printer comes with a cyan, magenta, and yellow cartridge, and then also an additional black cartridge to help fulfill the true black tones. Now, if I mix cyan and magenta from your printer together, I get the color blue. And then if I mix cyan and yellow together, I get the color green. And if I mix magenta and yellow together, I get the color red. And then if I filter out using all three of the filters, I get no light or no color, which is black. Now, this is a nice little pretty drawing, but if you see an additive spectrum over here, this is an actual additive spectrum. And you can see that we actually do get these combination of colors. So you have magenta, yellow, cyan, and green, red, and blue, and then in the middle you have white. Now those are the colors of light. So let's talk about how do we see. Now we see colors based on certain colors reflecting off of objects and others getting absorbed. If I'm looking at a red object, then that means that the object is absorbing all colors except for the ones that are of a reddish tint. Now here I have a gentleman who is wearing an orange sweater, and you can actually see down here this orange shirt that he's wearing. And he's standing in front of a spectrum of colors from violet over here all the way to red, which is the entire spectrum of color. And he has this different color plate right here that has many different colors on it. And so whenever he's standing in front of the red color, what you see is his shirt still kind of orange, which it is. But then you see these colors in a particular hue. Now, as he moves over to the green area of the spectrum, you notice how his shirt no longer is orange. That's because there's no longer orange colors being projected at him, and so they don't bounce off and reflect into our eyes. So his shirt looks gray. And all of these colors that were once orange up here are now appearing to be green and yellowish and even a dark bluish. And then as he moves over into the blue part of the spectrum, we see that those colors are, once again, into the darker realm of blue, and you even have a purple here. And so his color, what we see as color, is just merely a reflection of the color that's hitting the object. If we don't see the color that the object is, or the object looks gray, it's because it's absorbing all the light that it's getting, and whenever it's reflected back at our eyes, we are not seeing the actual color. So let's talk about refraction and what refraction has to do with color. Now, refraction is the bending of light. So let me get a pencil here. Refraction is the bending of light as light travels from one medium to another. Okay, and by medium I mean the stuff that the light's traveling in. So here I have a gentleman sitting in a swimming pool, and if you look here, let me go ahead and make this larger so we can see. The light is, get out of here, you don't need you right here. The light is traveling from the medium in the air, all right, which is coming to our eyes, and then it strikes him. Now the light from him, it reflects off of him, and then it comes through the water and out this glass. So it goes from the water to our eyes. Well, from what we see without the refraction, the gentleman's head is at this location, but due to refraction, his body appears to be over here, and it looks like he's holding his head up. But in actuality, that is just bending of light, and it's an optical illusion. His hand's actually still holding the sign right here, not really his head. Don't freak out. So now we're going to look at what causes refraction. Now refraction is caused by the light trying to maintain its maximum speed. Okay, so it wants to go the fastest from one medium to the other. Now, in order to simplify this, we can look at a scenario where we have a lifeguard on duty and we have a person drowning in the water. Now the lifeguard has to get from his stand to the person in the least amount of time. Now we often say that the least amount of time is the direct path. So if he starts here and he goes straight to the swimmer, well, that has the least amount of length, but because, here's the situation, the lifeguard can run faster on the sand than he can swim in the water. I know, what kind of lifeguard can run faster than he can swim? He's not a very good one, but still, we have this situation now where he has this very little amount of time on the sand where he's going the fastest, and the majority of his time is in the water when he's going the slowest. Okay, so least distance, but still not the fastest time. Well, there's a couple other ways that the lifeguard can take. The lifeguard could take this path. He starts here, and he spends the maximum amount of time on the sand and the least amount of time in the water to get to the victim. Okay, well, that spends the most of his time when he's going the fastest. Okay, but then a little bit of that time is whenever he's going slow. So he has the least amount of slow time. But the thing is this distance is a lot longer than this distance. So is it the fastest? No, it's not. And then you have like the complete opposite, which is totally not even going to happen. And that is where he spends the most amount of time when he's in the water and being slow. And so this pass is definitely the slowest that he could take. Well, light tries all three of these different paths simultaneously, and then it picks the fastest path to take. Now, it's not any of these three. Instead, this is the magical thing about light, is it picks the one that's going to give it the fastest time. And so here, let's start with this line. Let me pick a line. Now, light, the fastest time is to maximize the amount of time it's going to be on the sand, but still keeping its distance shortest. And so the blue line here is actually going to be the fastest line. So in order for the lifeguard to get to the victim the fastest, he has to bend his direction. He can't go straight through. Now that's kind of a lot of conjecture and a lot of theory based on that, but it actually comes out to be true. And so if I get rid of all these bad paths, so delete, delete, delete all these slow paths, and leave the fastest path, we see that his path ends up being curved. Now, like I said, it's full of conjecture, but it is something that we observe to be true, is that light is smart enough to pick the fastest path. Now, the same thing happens when we talk about light as particles going in from one medium to another. Now, light outside in a vacuum actually travels quite fast. It travels outside in a vacuum, or also in air, I want to include, that the traveling of the speed of light is c, which is 3.00 times 10 to the 8 meters per second. Now, that is fast. That's super fast. All right? As a matter of fact, it takes light from the sun 8 minutes to travel to the earth. Now, that seems like a long time, 8 minutes, but that's 93 million miles in 8 minutes. So in air, so let's say this is air over here, light travels at this speed. But in this medium, so let's say that this is glass. Okay, well, light travels much slower in glass. And so what happens is, if these are our light particles and they're all even with each other and they're all traveling at a constant speed of 3 times 10 to the 8 meters per second, well, at equal time intervals, they are at the same distance away. But as these particles start to become incident on the glass, which means they start to strike the glass, then the parts that hit the glass first slow down first. And so this one slows down, and then as we go along a little bit further, well, this one has slowed down, but these have kept traveling. And eventually, as they all slow down, it causes the wave to turn. Now, like I said, the wave or the light is trying to make it through the glass as fast as possible. Now, we relate the speed of light in a medium to what's called an index of refraction. So, index of refraction. All right. Every material has an index of refraction. We just usually use experiments to find that out. And we're going to do that in this unit. We're going to find out the index of refraction of various items. So you have the index of refraction, and that is given by the variable n, and it is just a ratio of the speed of the object inside a medium to the speed of light. So that's the speed of light, c over v. So it's the ratio of the velocity of the object in the medium, or the velocity of the light in the medium, to the speed of light of the speed of light in a vacuum. So this is called the index of refraction, and this is one of the equations we're going to need to use to relate how fast an object, or not an object, I'm sorry, a photon, a beam of light or light travels in a medium. Now there is a very awesome phenomenon. Now we say that light, nothing could travel faster than the speed of light. Well, that is true, the speed of light in a vacuum. But because light slows down as it travels through different mediums, then there is an effect called the Cherenkov effect, which is where, because light travels slower in water, then we can actually have particles traveling faster than light in water. We see this in nuclear reactors. That's why fuel rods glow. And that's because they emit particles that in the water that is cooling down the fuel rods are traveling faster than the speed of light in the liquid. And so they create what's known as, or what's kind of like a light boom, right? Which means that the particle is overcoming the light reflecting off of it, and it causes it to glow. And that's very fascinating. And you can actually look pictures up of the Cherenkov effect on the internet and do a little bit more research on your own. So we have this index of refraction. We need to learn that, or we need to keep that in mind whenever we move on to the next section. So now we want to make predictions and calculate refraction. Now, being able to calculate refractions, we can actually apply this to a lot of practical means, such as eyeglasses, binoculars, telescopes, aquarium bubbles, anything that it deals with light traveling from one medium to another. Now, calculating refraction was actually discovered by a guy by the name of Snell. And so this is going to have the name of Snell's law. Now, Snell found out that if we were to compare angles before and angles after refraction, then they come together in a very nice equation that we can use to calculate. So in order to do that, we have to define some things about this ray. So here I have a red ray of light that comes in, and let's say that this is air. All right, and over here, let's say that we have water. Okay, so light comes in from the air, and then it travels into water. So we're looking at light going into a glass of water or light going into a swimming pool. Now on this side, we said that the velocity of light in the air is actually pretty close, or exactly c. So that means the index of refraction on this side equals 1. And so we're going to call that the index of refraction 1 because it's the first side, or where the light's originally at. Now over in the water, you have the index of refraction, which we're going to name 2 because that's the second place that light is, of 1.33. All right, so that means it's about a third more of the air. Now, so now we've defined that we have a speed of light ratio, or the index of refraction for one side, and then the index of refraction for the second side. Now what we want to do is we want to look at a normal line to this surface. So this is the surface of the water. As light comes in, or we want to define this line right here. This is the normal line. It is perpendicular to the surface. So it's perpendicular to the water-air surface. And then from that, we can actually define our angles. And so we have this angle right here, which we are going to call the angle of incidence. So this is, we'll call this theta 1, and theta 1 equals the angle of incidence. Okay. Now, this angle from the normal, or from the perpendicular line, we're going to label theta sub 2. Now, theta sub 2 equals the angle of refraction. Okay, so we have an angle of incidence and an angle of refraction, and they're measured from the normal line. Now, Snell put all of these things together in one very nice law to help us predict what these angles are and what the index of refractions are. He came up and said, well, you know, if you take the index of refraction of the first side, so in this case it's air, and multiply it times the sine of the angle of incidence, then that's going to equal the angle of refraction for the second side, or the second medium, times the sine of the angle of refraction. So this is going to be theta sub 2, this is theta sub 1. And so n1 sine theta 1 into sine theta 2. Now this works for one scenario. And once you find this, you can actually, if you have another line over here, you can figure out how it's going to leave this water. But this is Snell's law. And we can use it to make awesome predictions about the way that light bends inside mediums. Now let's look at the splitting of light. In that first picture, we saw that a white light ray came in and we got colors out. Well, that's exactly what we see. And this is the function of a prism, is to separate light into its different colors. Now, looking at this prism, I have a white beam that comes in, and then as it refracts through my prism, I get a colored beam that comes out, or multiple colors. Now, there's one thing that I should notice from this. And the reason is that why this light splits like this and gives us a rainbow is that colors refract differently. So red refracts less than violet. So it bends less than violet. Now that's important to know. That means that if we figure out the angle of refraction and then subsequently the index of refraction for red, it doesn't necessarily hold true for violet. So we have to find index of refractions of different light waves, different colors. So one thing that I want us to glean from this is that colors refract differently, and you have to have a different index of refraction for each color. Okay? And that's all. All right, hope you enjoyed this, and get to calculating.
That's all, folks.